Hello, everyone. This is lecture 16 of PTRE 465531 Petroleum Reservoir Geomechanics. Today we should wrap up Module 2 and get close to wrapping up Module 2. Nevertheless, not the entire Module 2 is going to be on the exam. We are the exam will cover about roughly, I will show you when we start reviewing on Monday, but it shouldn't cover much more than, let me change the lights here. Oh, slightly better. Let's see. I haven't done the exam yet, but I will say, let's say that it's going to cover up to the compressibility. Where is it? Just like I did last year. Just before we start talking about anisotropy, here, this slide is a good end. The deck I have is slide number 40, where it sort of summarizes and puts together a general solution for any linear elasticity problem, which involves force equilibrium, kinematic component, constitutive component. That's where the material for the exam, will end. Okay, so you only need to study up to this point. But today we will progress from where we stopped last time. And I know I went through stuff very fast last lecture. I will go through it a little bit slower today and move on a little bit. And I think we're going to get close to the end. We have poroelasticity and one more, thermal effects. And then we are done with module 2. Monday and Wednesday is going to be review ahead of the exam. You have one office hours on Tuesday. And also I'm available by email, etc. The exam will be a 50 minutes exam on Friday. And I will make sure that it's something that can be done in 50 minutes. So don't worry about that. But you need to have very good understanding of the material covered in the class to be able to do good in the exam. So don't come unprepared. Don't just watch the reviews and think that you are going to be ready. Don't just go through the homework and the example problems and think that you are going to be ready. You need to do everything together and you need to master the material, basically. That being said, it doesn't mean that the exam is going to be hard necessarily. It means that it's going to basically show if you guys know or don't know, which is the purpose of the exam, to be honest. And I know this module is a little bit intimidating. Oh, and I decided to make your life easier. No matrix rotations in the exam. We might see eigenvalues, we might see eigenvectors, but we are not going to see RPG in the exam. So don't worry about those. This is like if you set up your matrix right, this is really what I want you to know. Be able to set up your matrix right, and then you can do the question maybe in MATLAB or Mathematica software of your choice. But once you set up your matrix correctly, after that, it's a person pushing exercise. So it just takes time to do it. It might be weird values, but it doesn't mean that it's not really a geomechanics problem after you set up your matrix, right? And also in the homework, the eigenvalues and eigenvectors that you saw problem, all of them were unstable. So those were a little bit harder than what you expect to see in normal life, because in normal life, you have stability. To have stability, you have diagonal symmetry. Yeah. So don't Like, yeah, the homework problems that you saw was a little bit on the harder side, both conceptually and mathematically, so time-wise. But in the homework, you had like a week to do or something, like a lot of days. In the exam, you only have 50 minutes, so I also need to be smart and know what I'm asking. Yeah, we did talk about, so slide 40 of module 2, that would be your, we did talk about anisotropy last time, and we said that it's basically differentiation in the properties, in the mechanical properties with direction. Tropos comes from the Greek word tropos, which means, it really means method, but it also means way, direction. So you look at one direction, properties change than another direction. And we talk about two models of anisotropy. How do I go from isotropic model, what we have seen with Voigt's notation? How do I go to what we call VTI, vertical transverse isotropy, which is the easiest, one of the two easy anisotropic models we can think of. And it's very good for rocks. That's the model with the many floors, different color of each floor. So you are in each floor, you see the same color, but it's a different color as you go from one floor to another. So we talk about that, and then we talk about orthorhombic symmetry, which is basically an isotropy in X, Y, Z. So X is one value, Y is one other value, Z is another value, but I can move around the model, and every time I see an X, it's the same value. So 3 colors for the whole thing. And we applied that mathematically, or we saw how it is applied, and remember, I forgot about those two are interconnected. So you have 6 different non-zero parameters, but you only need 5 for the VTI, and you need 9 for the for the orthorhombic. This is an important slide, but the slide 42 is not going to be on this exam.
So the VTI is like not something like the tortuosity. It doesn't include like change in one direction, right?
Let's see. Change in one direction?
Like,
no.
Not like
the change only happens in the, if you are looking, only if you are looking at one direction, you see change. Everywhere else, you see the same thing.
Okay, so it's not like in the reservoir, you have some time tortuosity where the permeability change from different areas, something like
That's
that.
heterogeneity.
Yeah.
Yeah, that's different. That's here I have one model, there I have another model.
Yeah.
That's heterogeneity. It's heterogeneity and isotropy is different. Heterogeneity means I'm different in one location than another. Heterogeneity has to do with geography, like geographical location.
Yeah.
Whereas isotropy has to do with direction. The key word for isotropy, I remember from when we were doing Petroleum, the key word between, it was like they are using, if you go to the Schlumberger glossary, it used to be called, well, it's SLB Energy Glossary right now. It used to be Schlumberger Oilfield Dictionary when I was young. And they were getting a lot of questions from there. And we tried to find keywords for those, the definition. The heterogeneity and anisotropy was very similar definition, but the keyword in that anisotropy was direction, variation with direction, variation of properties with direction, and with the heterogeneity it was location, if I remember well. I'm not sure if it was saying anisotropy was direction for sure. Well, anyway, I need 5 for transverse, VTI, vertical transverse isotropy. I need 9 for the other thing, orthorhombic. Again, these are important, but they are not for exam 1, right? Maybe they are important for another exam. But yeah, now, okay. We said linear elasticity. We talked a little bit about anisotropy, not a lot. we talk about heterogeneity too. But okay, what is a material that behaves a lot linearly elastic is, I don't know, this desk. I bet you it's very linearly elastic, the way it behaves for small deformations. What if I compare this thing that I know it behaves very well as a linearly elastic with rock? What we said is a different thing that the rock has that this thing doesn't have.
Different material.
So,
Porosity,
yeah, what is that?
the pore pressure,
Yeah, but
volume, you have another material.
yeah,
Liquid.
you have fluids
Fluids,
inside the pores.
Yeah.
So you have pores, and the pores have fluid, and the fluid is under pressure. That's how I get the PP, which I added in the model. Remember, I made the changes. So Malek is very correct when he said that you have porosity, you have fluid field porosity, basically. And we said how we incorporate the fluid model in my system. It was something like, I think I drew it as, let's write it. Where is it? Sigma equals S minus PP I, and that became matrix equals to matrix minus PP identity matrix. And then you have whatever, sigma, 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 1, 1, blah, blah, blah. This is 2, 1,
No,
or 1, 2.
no.
Yeah, this is 2, 1, 3, 1, 2, 2, 3, 2, sigma 2, 3, sigma 3, 3, and then you have the same basically. Yeah, 1, 3, 2, 3. Awesome. So yeah, this is the identity matrix. This is the matrix I.
But your PP is not one.
Yeah, it's a Viking. It's a scalar Viking, right? It acts in every direction, so it affects only my normal stresses, not the shear stresses. Okay, so that's a deviation that we have from linear elasticity. So we take the linear elasticity and we add pore pressure in it. We modify the theory, the mathematics, to incorporate pore pressure. And we are basically making the model more applicable to rocks. It's not perfect. It's not perfect. It's not the only thing I have with rocks. That, by the way, I'm in the wrong slide. It's not the only thing I have in the rocks that makes it a little bit different than linear, makes the model potentially deviate from linear elasticity. The thing is that those pores that are filled with fluid are interconnected. And there could be a possibility that the pressure in some pores is bigger than the others.
Sure.
Okay, so that makes it even more complex. Then I have fluid wanting to move from high pressure to low pressure. I have a pressure gradient. Or maybe I have a wellbore, and the wellbore is interconnected with the pores. The pressure in the wellbore may be different than the pore pressure. Okay, so now I have fluid that wants to move from high pressure regions to low pressure regions. And I want my model to incorporate that somehow. We call that pore elasticity, the elasticity of the pores. And that has to do with, as the pressure moves, as the fluid moves from high pressure area to low pressure area, the size of the pores change. So where the pore pressure increases, the size of the pores gets bigger. Where the size of the of the pore pressure decreases, the size is getting smaller. And we are playing around like this, okay? I have an animation that actually I made for my PhD defense back in 2022, and I changed the colors. It was LSU colors, I made it UND colors since, but is it gonna work? Yeah, when the rocks deform, most deformation transfers into changes of porosity, okay? Fluid flow in and out of the pores induced by pressure variations, e.g. pressurized wellbore nearby, making fluid go from the wellbore into the pores, can alter the size of these pores through elastic deformations. And those effects are dynamic, they are time dependent. Let's see, is it gonna work?
It's fine.
No, it's supposed to, they're supposed to get bigger slowly.
Yeah, it's fine.
No, oh, come on. Okay, what about now? There you go. So you see, the PW gets bigger a little bit before the pores get bigger. It's trying to show you that, okay, I increase the wellbore pressure, then the pores around the wellbore start getting fluid with bigger pressure.
You're increasing.
Yeah, or decreasing the
Ah.
same way. If it's if I'm decreasing, fluid goes from the pores into the wellbore.
Or increasing, injecting.
Yeah, basically. So it actually, the pores further away from the wellbore will respond at a later time. So, okay, this is also a time-dependent effect. So I might be, there is a lot of modifications I need to do to my model to incorporate all that. We talked about compressibility. You understand that the compressibility of the rock material plays a role. The compressibility of the fluid inside the pores plays a role. The compressibility of the fluid inside the wellbore, if there is a wellbore nearby, also plays a role. A lot of stuff. So those are mostly dynamic stuff. In Greek, dynamic means power. In English, when you see dynamic, it means time dependent. Time dependency. So we are going to incorporate our models in a very weird way after Terzaghi. Terzaghi was a soil mechanics guy who studied in UNAM, the Mexican University. He did his PhD from there. UNAM is very famous for doing very well in Petropol year after year. They take Petropol very seriously because those kids there, they really want to get a job that is not really working for their national oil company. So because they graduated, they go to work, I guess, for local businesses. It doesn't necessarily mean the national oil company, but it's a very low pay. So they are doing whatever they can to improve their CVs, to get into better schools or go do better. So for years, they have created systems to help themselves, like make a better name for themselves. And one of them was like to take Petropol very, very seriously. To the point that I remember when we beat them in the regional of 2018, they were the reigning champions. And they had a bye to the international. Doesn't matter, as long as they show up, they compete, they are gonna go there. It doesn't matter if they lose in the first round or something, because they have an automatic spot in the international. And we had to beat them to progress and qualify. I was with Texas at the time. And we had a terrible game. Like it started, I think we got the first question, we were ahead, and they were ahead, and then we won. And I think the last question, even if we didn't answer and they answered it correctly, we would have still won. So I told the judges, you may not ask the last question because it won't make any difference. Anyway, and after that, I went there to tell them thank you and everything, and they were crying, right? They were crying. I mean, they were crying and they had automatic admission. Imagine how important it is for them. Anyway, I think they have an retired professor who worked with Schlumberger, and his whole job the whole year is to do Petropol. Yeah. But it helped me the next year because they saw me with another school, and then they were.
Because you went from your T to.
Yeah. So yeah, yeah, they won like many times. The first time they won Petroleum was 2015. And I was in the final with Texas. They beat Texas in the final. What was it? 55-25. It was a very close game. There was a moment in that game that both teams had negative score. Believe it or not. Anyway, but bottom line is Terzaghi went to UNAM. He did a PhD. He was a soil mechanics guy. And he took a theory of linear poroelasticity by Biot, which is a French guy from 1924. I think it was 1942 when Terzaghi did that. Sorry, no. Terzaghi did that in 1924 or 42, but Biot did that in 1904. Well before that. Something like that. I might be getting my years wrong. But Terzaghi came after Biot, and he took his equations, his theory, because it's a very big theory. Like Biot put books together about poroelasticity. Like the math of poroelasticity are crazy. Like I cannot follow those. But he took poroelasticity and he incorporated it into the matrix in a certain easy way. And he basically did this. Okay, we saw that. We're gonna see that a little bit later. I want to show you. We're gonna do this. Sigma. I'm gonna show you where we are heading, and then I'm gonna show you how we got there. Sigma equals S minus, we had this, right?
Yes,
Now I'm gonna have this,
the Biot constant.
the Biot's coefficient.
Coefficient.
Yeah. And this alpha B varies from 1 to 0, and is the Biot's poroelastic coefficient. Sometimes it's mixed with Poisson's ratio, and it makes another, for simplicity, just like we have the plane strain modulus, we mix it with the Poisson's ratio, and we have another term that is given by capital A, which is called the Biot's poroelastic constant. That's a different thing. That's a made-up term to make the math simpler, sort of like the plane modulus. But Biot's poroelastic coefficient tells us how flexible, how easy it is to compress the pores and make them swell and shrink as the pore pressure inside them changes. And this is not a very accurate, I will use a bad word, I will say exact. People don't like the word exact because not many things in math and science are exact. But this is very, very far from exact, right? This is not a very accurate thing, but it's good enough for us. And think about it, okay. For rocks, Biot's poroelastic coefficient is something like from 0.6 to 0.951, for instance. Something like that. For shales, when you have water and they can compress a lot, is basically they can go up to 0.3. But nobody really knows what is the Biot's coefficient of rocks, in all honesty, because it's very, very hard to come up with an experimental test, laboratory test to measure Biot's coefficient. But the closer you are to 1, the closer you are to like a rock that doesn't deform at all, the pores stay as they are. Okay, change the pressure as much as you want, it will be fine. The closer you are at 0 is to a rock that deforms like entirely.
Mm-hmm.
So where you have shale, clays, you have water. The water makes them expand and contract a lot. So pore pressure has a big impact in them.
Mhm.
You are close to zero. Mark McClure says that some measurements they did in rocks for shales for Poisson's ratio. I don't know if it was Mark McClure who said that. Somebody from Stanford said that they were getting readings up to 0.3, 0.4 for shales. And what we learned in class is that for rocks, typical rocks, 0.6 to 1. So 0.3 was very low for us, you know, but it can apparently get that low. Nassim has who was taking this class last semester, my graduate student Nassim has a model that is analytical for fracture initiation from perforated wellbores. And it's analytical, but it's an approximation. It's not certainly not an exact model. It's a closed form approximation. And he found that the Biot's coefficient, if we go that low, it causes quite a big impact. When I was in my PhD, I was more like, okay, Biot's coefficient, 0.6 to 1, not much change. So ignore it. Yeah, I was like that. But it's not the case, actually. It might not be the case in things that we are interested these days. Significant in tight rocks with high stiffness and low and unconductive porosity. Okay, I agree. When rocks deform, most deformation transfers into porosity changes. As a matter of fact, the solid phase can also deform and change volume, yes. Because that's what happens basically when the pressure, the changes in the pore pressure induces the change of the size of the pores. It makes them bigger and smaller. So that's what it changes the size of the pores, makes them bigger when the pore pressure gets bigger. The stress deformation relationship is corrected using Biot's poroelastic coefficient. And this is the actual definition of the Biot's poroelastic coefficient, is the ratio, 1 minus the ratio between the drained and undrained bulk modulus. Remember what is bulk modulus is the inverse of compressibility? Is I change the confining pressure, the volume changes a certain way. What would be different when it's drained versus undrained?
Drained, pore pressure is very low. Because you don't have like here, you already like drain the area, there is no fluid on the pores.
Okay, undrained.
It's more compressible because it's
Yeah.
Can we talk about drain and undrained in terms of speed of the test? If I'm testing this in the lab, if I do the same test fast versus slow, fast would be what? And slow would be what? Fast would give me an idea of drained or undrained.
Fast. About what? Compressibility?
The same rock,
what is
same
fast?
fluid.
What's fast in the test?
What's fast, like compression?
Yeah.
No, compression, it will not give you,
I don't let enough time for fluids
Yeah.
to leave
Yeah,
the rock.
yeah.
So am I undrained
And drain,
or fast?
yeah,
And for slow,
you drain, yeah. you're
I'm
drained.
drained, yeah. Yeah, very nice.
And drained is more compressible because you have not pore pressure inside.
Yes, it will change.
Yeah, you will have two readings different.
Yeah. And because it's more compressible, what does that mean? The bulk modulus is smaller.
Yeah,
So
more compressible is the reverse way. Compressible is like it deforms.
okay. So which bulk modulus you expect to be higher? The drained or the undrained?
The bulk modulus.
Yeah. Which is the inverse of compressibility.
Yeah, sure. But I'm trying to remember what you told me last time about compressibility. Is like the more it deforms,
Yeah.
it's less compressible.
It's the more it deforms, the higher the compressibility.
Okay.
The undrained has to be more.
Yeah.
The undrained has to
Yeah,
be
otherwise you
undrained bulk modulus.
You will have the negative
Yeah.
bios.
Because
Yeah, but from the logic of physics,
No.
Like,
Because it's the inverse of compressibility. So,
okay, if this is bigger than this, which has to be,
yeah.
which one has the highest compressibility? If this is bigger than this, it means
So-
that this has higher
Yeah,
compressibility
yeah,
than this,
yeah.
which is logical,
Yeah,
right?
the
If
reverse.
there is no fluids there, so, or think about it, I compress it, I give more time for fluids to leave the system. So, yeah.
I'm joining my compression.
yeah, this is one way of thinking about it that sort of makes sense to me. Typically for rocks, 0.4 to 0.9. We used to say 0.6 to 1, basically. You can go up to 1. The thing is that because it's not a fully mathematical adaptation, many times, many people think that if you put 1, you go entirely to linear elasticity. Not always, not always. In some places, for instance, if the wellbore pressure and pore pressure are equal to each other, we're going to see that in later module. Yes, you go back to linear elasticity. But if there is a difference between the two, they are not the same. So don't expect that, okay, if I set my alpha b equals to 1, it means that I need to be getting exactly what I was getting in linear elasticity. Not always.
But that means that the bottom use of drain is 0.
Yeah. Yeah, it's very unrealistic.
Which means like it's
You can compress it to nothing, basically.
to infinity.
To like,
Yeah, you can compress it to basically nothing. There is no fluid there.
Like you have infinity of compression.
Yeah, because if this is,
So when you go
Infinite compression.
yeah, infinity
Yeah.
compression.
yeah, I mean, obviously it's a way of
mathematically, yeah, I understand. It's,
yeah, P represents the lowest possible alpha B. So you cannot compress more than, you cannot get more than the amount of fluid outside of the fluid that you have in the pores outside of the system, right? Like if I have a sponge, I cannot get more water than the amount of water that is, the volume of water that is occupied, right? That's the idea here. Obviously here, okay, if I set alpha b equals to 1 in this equation, I do get what I had before. Okay. If I set this equal to 1, I do get what I had before. But it's not for everything. Like if we do the model for the near wellbore stresses, don't expect to set alpha b equals to 1 and get the same answers, because it's like assumptions with assumptions. It goes on, it's crazy.
and that's ironic when you talk about above 1, it's impossible. Because, sponge of water, for example,
Yeah.
as you said, we have like a proverb in our country which says like the person that like that doesn't have the thing that you're looking for doesn't expect that he will give it to you.
Oh, yeah. It means that, okay, if I have this volume of, if my porosity is 20%,
Yeah.
I have 20% fluid.
You
I
will
cannot
not-
get more than 20%
Yeah.
fluid out of the rock.
Yeah,
I
you
don't
don't
care
have
how
30.
much I compress it.
Then we don't need production.
Yeah.
Just need sponge of oil. Every time you press it, you get more.
Yeah, that's the idea. Basically, it's a mass balance.
It's like a renewable.
You violate physics
Yes.
after that. Yeah.
Sustainable renewable.
They will get mad at us, the old people in those stuff. They will get mad at us, please.
Yeah, you cannot go lower than the porosity. And okay, any questions on the poroelasticity? Right now, that's how much I care about you knowing about poroelasticity for this class so far. We may see a little bit more of poroelasticity later on. We will actually, and then we are gonna see more in the next class, as in 475 or 575, which is the well completions. The next class, but yeah, this is, and maybe I should have titled this slide linear poroelasticity, Poroelasticity is like a topic. You can do a PhD on a branch of poroelasticity. You cannot do, nobody really knows everything about poroelasticity. Is very, very complicated. And actually, I know I was saying that Biot should have done this in 1904. I'm not sure exactly when he did it. I don't remember when is the Biot's reference that we do in the papers? 1904? Because I read my own advisor showed me she has like a series of books on poroelasticity on her desk. And it was written by a Chinese guy, and the Chinese guy has a picture with Biot's wife, widow. They are like he went to visit her, and she's an old lady, obviously.
Colorful picture or not?
It's a colorful, it's a young guy, but he's like a big professor in something like geomechanics or something, or no, might not even be rock mechanics or something, and he has so let's just say his widow was alive maybe last decade. So I don't think, was it 1904?
1956.
No, that's too late. Just Google Maurice Biot. When was he born? When did he die?
Yeah, Maurice was, they said in 1956.
He was
Maurice
born.
Biot wrote 2 articles where he proposed a theoretical formulas to describe the elastic wave propagation. And one of them was the BIOS.
So, but I think
Yeah, it would be something.
yeah. Anyway. No, it was before that because Terzaghi came either in the adaptation of Terzaghi, the Terzaghi approximation, as we call it. That's why it's not exact, it's approximation. It was 1924 or 1948, and it was a book titled Soil Mechanics. It was a purple cover, if I remember well. Or I saw it somewhere. Yeah, I saw it somewhere. Okay. What about other stuff that can impact the model, the rock, that maybe you don't find in the linear elasticity? Huh?
Temperature.
Yeah, for sure. Oh, yeah,
Let's see.
put, yeah, thermoelasticity. Yeah. Temperature. Now that the temperature is a little bit easier than poroelasticity. It's a little bit easier to model, especially, which is counterintuitive, in cylindrical coordinates. In cylindrical coordinates, we are gonna see that maybe in module 4, module 3, or module 4. No, module 4 in this class. It affects only one of the stresses. In Cartesian coordinates, it affects every stress, but it's okay. It's not terrible. The thing is that we can make the adaptation mathematically, whereas with poroelasticity, we need an approximation to help ourselves, to make the model good enough. It's not like good, you know? So if I have thermoelasticity, it means that changes of temperature in solids change the equilibrium distance between molecules, and therefore they reduce the strains, and vice versa. Like you can increase the temperature, the molecule distance goes apart. You decrease it, it goes closer. It goes on like this. Obviously, it will affect my system, and I need to incorporate that. I know that in classes so far, you have seen the thermal dilation coefficient, which is something in units of per meter, something like, oh, sorry,
Dilution.
per degree Celsius.
Dilution.
Dilation. Linear thermal dilation coefficient, something like that, which is if I hit something, it becomes longer in one direction. Huh?
Not just the
Oh,
dilatation, dilution.
yeah. We, yeah. As a solid is heated up, but not allowed to dilate. If I, okay, I'm heating up the solid. Think about it as a one-dimensional thing. So don't worry about things up and down. Worry about things only in this dimension. I heat it up, it becomes longer. What if I put something here and don't let it? It will apply stress on this, and then this will apply stress back. So I'm inducing strains or stresses. So it has to be incorporated in my model. It does induce stress and deformation. What do we have here? A solid heated up but not allowed to dilate in vertical direction, let's say, in one direction, doesn't have to be vertical, results in increased stress in the same direction rather than deformation. So the material wants to deform when you heat it up or when you cool it down. If you don't let it, you induce stresses. It's like the Poisson effect, sort of. But for this, it changes in the same direction. The thermal dilation coefficient, what we are talking about, quantifies strains induced from a temperature change at a constant pressure. So if I have a material of length L, and I heat it up, and it wants to elongate to this dl. I heat it up by dt, the change in temperature. I can calculate alpha t by this equation. It was L, it was heated up by dt, delta t, or del t, and elongation del L, or vice versa for cooling. Okay, but this is in one dimension. What about if it's a 3D object, or if it's a 2D object? We need to adapt it. We need to adapt our matrices for that. So typically for rocks, 5 to 10 times 10 to the minus 6 per degree Celsius. Logical. Can you convert that to Fahrenheit? If I give you the degree Fahrenheit conversion, 5/9 parenthesis, no, 9/5 degrees Celsius, parenthesis degrees Celsius plus 32 or something. You would be able to change that, right? Yeah. Yeah. So maybe important for the future.
Yeah, Fahrenheit.
Yeah. Under unconstrained displacement, oh, we have time. Conditions, a temperature drop causes shrinkage and a temperature rise causes dilation. You know that. The elastic equations extended to consider thermal changes make explicit that when you hear explicit, think analytical. When you hear explicit in the classroom, think of analytical stuff. That stresses can be changed as a result of a temperature change, delta T, via Voigt's notation. So what this says in a few words is I want to take the Voigt's notation, the matrix, and incorporate this delta T stuff in it somehow. And I'm asking if this is possible. And then you have thermoporoelastic couplings made possible. If I can make the matrix adjust for those. Here you are. It affects only my normal stresses. It basically acts like the pressure every direction. But what if I have an isotropy? What if this? What if the alpha t in one direction? What if this is in one value? This is another value. This is another value. It's possible, right? It's not impossible. So basically, I add 3K 3 times the bulk modulus times the alpha
You
T.
mean in the reservoir?
Oh, yeah, for anything.
How big is?
You may have an isotropic material, you may have layering in the rock, and the layer,
Or maybe you have
Phase one.
magnetic chamber or something like,
yeah, you have change in direction. In this way, you get more dilation than Y or Z. It's possible.
okay.
It's possible. It might not be important for you in the sense of like maybe the changes are not enough to affect the problem that you are working on, but it is possible. And if that's the case, you need to incorporate the right values into your system or the matrix system for the Voigt's notation. And remember, just like pore pressure, it only affects the normal stresses because it acts in every direction. It doesn't affect the shear stresses. Thermal stresses can cause fracture gradient reductions when drilling with a drilling mat that is colder than the rock. Thermal stresses can also cause slippage along pre-existing faults, which is earthquakes. We're going to talk a lot about that in the next module, a lot about those. PEF, pre-existing faults, PEF, P. Everywhere in the rocks, there is faults. And there is an assumption that there is an infinite amount of faults, and they are facing an infinite amount of directions. So, and they are pressurized or stressed at an infinite amount of values. But because there is infinite, it means that if I inject there, and the worst case scenario for a fracture to slip is being oriented that way, pressure at that way, stressed at that way, facing one direction, blah, 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 and being there in the first place, because of the low probabilities that I will find something there that can slip. It's we call it the critically stressed faulting criteria assumption, hypothesis. Sorry. We're going to talk about it in the next module, of course, but having thermal effects, it can impact whether these pre-existing faults will slip or not slip. Now, if it's a small fault and it slips, okay, small earthquake, I don't feel it. But if there is a bigger fault, it can become a higher magnitude. In fact, we have ARMA, the last presentation, the Dr. Lundster from USGS said that the changes in pressure that cause fault slippage are of the order of bicycle tire temperature, 15 psi or something, which is very small. I bet you can get thermal induced stresses of that order very easily. So maybe you're injecting water, salt water disposal. You inject it maybe at the colder temperature, and you get the fracture, or you get the earthquake or not, or hotter, and you get it. Who knows? But they do have
Thermal shock, I said, yeah.
yeah. And of course, in geothermal reservoirs, like things that people are interested these days, if you want to drill on a rock that is 300 degrees C, which is a crazy amount, let's just say something more logical, but I know people are doing estimates for 300 C Celsius. Let's just say less. Still, you can have geothermal effects. Then you need to, you're drilling geothermal, you need to account of thermal effects.
Yeah.
You know, it becomes important. Next time after the exam, so next class is going to be review. The class after that will be another review. Next Friday, we don't have a class because it's the exam. 11. October 14, we are going to do example problem number 4 for this module. Okay, so Use this weekend wisely, study for the exam. No homework due or anything. Study very hard. And do a good job in the exam. And we will I'll be back on Monday for the first review. It's to your benefit if you come to the review having studied already, having started revising. Don't expect anything to happen at the review, like everything to happen at the review. Anyway, thank you very much. Have a nice rest of your day. Have a nice weekend. I'll see you next week.